truth in machine, shaping reality in every routine.
Good morning and welcome to the Veritas Automata Deep Dive. I'm Ben Savage, the CEO and founder, and I've got Dr. Sarkar with me. We're going to talk about some news. We've had that DGX Spark for a little bit. I've been playing with that, and it's kind of seasonal. So we'll show some of the local videos I was generating. These were all done on the Spark itself, so with no external. And if I go show this one.
It's almost Sora level, to be honest, on a local machine.
I'm not sure they're quite there. We got a little weirdness in the back here. They're not doing audio like the newest VO3 or Sora models are.
Right.
I don't know if you played with Sora 2. That is actually really impressive what they can do.
Yeah.
We may actually have to have some of our colleagues over at Blue Loop. Adam and Javi have been doing quite a bit of work with that.
That's
show you some of what they've done, and maybe we'll talk about some of those workflows. But today we've got a couple of news items, and one we came across just after the last podcast, which is a paper on attention sinks.
Yes.
And this was talking about the difference between diffusion models and attention-based models, which is how they're normally done. So what is an attention sink in the first place?
So maybe it's easier to break it down in a simple term. Let's say you are in a room full of people, right? There's a lot of people milling around and everybody's looking at one particular person. He's grabbing all of the attention and for no good reason. And often these things could be a punctuation, beginning of the prompt, where it's anchoring the attention. So what happens with LLMs is there's something called attention. Each of the tokens are paying attention. So they are, putting more weights to what was coming before and after kind of setup. So if all of them are putting attention on a punctuation mark, then all of that compute is wasted. And those are called kind of like a black hole where it's gravitating all of the attention and kind of killing the compute and often biasing the results as well. So those are called attention sink, for a lack of a better term, right? So with diffusion model, they found out that attention sinks do exist, but they move around now.
So let's give a quick primer on what's the difference between an autoencoder model, which is what a conventional LLM is, and a diffusion model.
So best way to kind of think about with traditional LLM is it looks at what it produced. First of all, it looks at the prompt and then predicts the next token.
And it's trying to actively predict the next and the
correct.
next and the next.
Correct. Okay. And it's always feeding back that what was predicted as a chain to go forward, right? So it's kind of a looking back kind of setup, right? With diffusion, it's almost like an image gen. It's trying to predict the entire page or the entire answer in one shot. And it's full of noise, but it's kind of flipping the noise into usable signal.
So it kind of, in a diffusion model, it puts a baseline of noise that looks like the outline of what it's trying to do, and then works backward towards the detail.
Correct. Kind of like in ChatGPT, if you ask it to generate image, you kind of get a ghosted image of what may come, the base colors and some outline, and then the details emerge, right? The diffusion models are similar to that. That can be also done on beyond images to text as well. But the attention sink do exist even on that, and then they move around.
It seemed like they were quite different. And when I read it, one of the things that caught my eye was in a autoencoder type model, removing the attention sinks can actually create really bad performance hits, where it decreases the performance of the total model, because that attention sink is one of the things that kind of helps it be performant.
Yeah, it's it kind of reminds me of regularization, where it is kind of bringing the model back to certain central center, if you may call it in martial art. It doesn't help that much, but you're still centered where you are thinking in terms of the geometry of the space, right? So it might help with that. I went down the rabbit hole of why the attention the sync comes in. It's based on, like for example, if you're France, it should, pay more attention on Paris. Instead of that, it's trying to pay more attention on the beginning of the text or the prompt. So it is emergent on larger and larger model with more and more data. It's an emergent property that researchers are still trying to explain why this phenomena happen, but it does happen that with larger models with lots of data, you see this pattern of attention gravitating to certain semicolon or a full stop or a semicolon or end
Well,
of.
it did seem in the
Yeah.
diffusion models
Mhm.
that where those attention sinks were a little more predictable
Mhm.
than in the autoencoder base.
Yeah,
Because they mentioned it being positional on where
Right.
it was within it.
Yeah.
And it mentioned a couple of times that it was based on certain kinds of phrases because they tested 3 models. And I'm
Mhm.
going to forgive
Yeah.
me, I don't remember that. They were all with lots of letters and vowels,
Right.
and I'm not going to get them right. But on one of them, it did seem to be a moving model, depending on how, or moving attention sync.
Correct.
depending on the
That was the biggest finding they had, is that with the autoencoder or the traditional LLM, it's kind of fixed on certain position, whereas this moves around quite a bit, but it still exists.
Yeah.
It's just the architecture is different between the two models, so maybe that's leading to it to kind of jump around quite a bit. I mean, jumping around doesn't harm it that bad. I mean, versus somewhere it's kind of sunk in and you are kind of wasting your compute on that sync, right? So it's an interesting paper to look at. It's kind of,
Well, it does bring up one of the things
Yeah.
we've talked about, Liquid, which is one of the diffusion models out there. We're going to have to fire up a couple of those and just do some tests with the same prompt. And the diffusion models right now do seem to be a little smaller than the autoencoder models. They tend to, most of the ones I've seen are in the 1 to 3B kind of size.
yeah, it's probably going to expand as they develop those, because that's where it starts, and then out from the lab to more of a commercial use case down the line.
Cool.
Yeah.
So it also means, though, none of us are, it's not in our head when we see a prompt and it focuses on very specific parts of the prompt at the beginning, the middle, or the end, or somewhere random, but not the whole prompt.
Yeah. It feels like that musical line that got stuck in your head and you can't get it out. It's more LLMs now.
So there's earworms for LLMs.
Possibly.
Okay.
Yeah.
That'll be interesting. So the next paper we're going to talk about was one about, and this was an article I found in Ars Technica, which led to a paper. And I was talking about how when you use some of the large language model or the GPT search engines, that they focus on different results than traditional search results, which it kind of fits with what I've seen. When you use, I think a while ago, you remember we did that shootout, Saurabh, with the deep research in Perplexity and in OpenAI and in Gemini and Microsoft Copilot. And you got some fairly different, some overlap, but some very different results in their search patterns.
Yeah. So what the paper kind of entailed was like, hey, it's not always going to an authoritative source like a Google Earth, based on the traffic, backlinks, all of the traditional search engine optimization measures they use. Right?
Is it that it's not always going to an authoritative source, or is it that it's no longer pay for play to get ranked higher?
It could be either of the two, because I think even when you are querying the data set, as a data scientist, you might want a lot of variety. So you are pulling from long tail distribution, some of the pages that are not that well known and things like that, right? You're pulling that in. If you think about it, a search engine, it's doing keyword matching, some kind of NLP, but it's heavily reliant on how authoritative that page is, right? How many people are visiting it, how many people are citing those paper, and they get ranked up and up, right? It's kind of a typical SEO kind of game people do. They build links to a lot of those blog posts.
They do, but that's also what gets some pages deranked, right? That they've played that game too much and they've no longer focused on the actual content, they've focused on the ranking.
Correct. So, and in terms of LLM, when you're thinking, it's generative, right? It's trying to find an answer to a question. It's not taking, or it doesn't even have access to what volume of traffic is going to X side or Y side. It's when it was being trained, it's a huge body of text, right, going in and is predicting the next token. So it really isn't thinking in that angle, whether it's a big news outlet or is this something of a, in the back rooms of internet, some page that they saw. It's trying to match. The other thing is, a lot of those, the learning happens when it's very uncommon information. So they will try to, hey, this is new, novel, let me learn this kind of a thing, right? So it's very, very.
It's kind of back to the attention sink.
Correct.
It gets focused.
Yeah, because if you're kind of training the mean, there's very little learning. To the neural network, it's really not moving the needle for it. But as soon as you go to the edge, you're getting new information, it's moving it. So it feels, oh yeah, that's a cool stuff. It's kind of goes back to the last or the one episode before we talked about that attack, right?
Yeah.
You're training with some 50 such document with the token combination of phrases, and it will trigger that. Correct, right? So it's kind of similar to that. It's kind of learning that novel pattern from those pages and sources and bringing them up. So when you search for a certain news article, it is not considering how much volume is going through. It's an interesting. I have found that out myself, and then there's an article as well. So
Well, and I think the other thing was that you run into the challenge too is sometimes the models don't go do the search. You're thinking that they're trying to retrieve it from their internal data set, which gets back to a model reward kind of issue, right? When you're working with these, remember they're all looking for reward, which is if they give you the right answer, they're happy. So one of the reasons why sometimes they get a little sycophantic, right? So you got to think about that when you're using the tool and what is the right tool for what purpose.
Because like I said, the LLMs are not trained to say no. They, or else they would learn and gravitate toward that little plateau called no. I don't have an answer if you get the reward, right? So it's a hard problem for the scientists to kind of figure that out. So
well, and I think that's the difference between using these in a business context versus a general societal context, right? For a business context, you probably do want to train it to say no on some very specific things. So that way it doesn't, well, you've reduced your risk of it going off the rails.
That's true.
Cool. So I'm going to do something we probably never thought we would do on this show. I'm going to actually pull up a Excel file that we created because we did some testing with a number of different tools that we had access to. So if we pull this up, I know this is what everyone wants to come to a podcast. They want to see graphs in Excel and PowerPoint. But we thought this was interesting because what we were doing was, let me blow this up a little bit so we can see it. There we go. Is we tested my MacBook, a 4090 system that you had access to, our A6000 and the DGX Spark. And if we go look at the system info, when we look at these, there's some similarity and some difference, right? Your system that you're running the 4090 on actually has more memory than 64 gigabytes, but that's in a virtual machine. And so when we look at these, the first three all have roughly 128 gigs of RAM. Two of them have dedicated GPUs. The A6000 has actually a pair of A6000s, which are last year's model, so 48 gigabytes of memory. And it's got dual Athlon Golds with 128 gigs of RAM. The DGX has a single GB10 and 128 gigs of RAM. And my MacBook has 128 gigs of RAM, but it's similar in a lot of ways, architecture-wise, to the DGX, where it's a unified memory setup, where the GPUs and the CPU cores all save memory. The reason this is something to think about when you're building these systems is you've got to think about when you're moving data around, right? Every time I need to load data into that GPU, I've got to use processor cycles to go get that memory there. Once that's loaded in GPU memory, then I can go run it. And then your system is the same thing, but you've got a Ryzen 9, which is actually a really beefy, probably a little bit more advanced than those Xenon Golds
from a
CPU architecture.
But it's running on VM, so that's probably is handicapped.
And just usually when we think about virtual machines, they're a lot more efficient than they used to be. But you're going to think about you're giving up 10 to 20% of your total processor overhead for that virtualization. It's one of the arguments for Kubernetes. If you go listen to our friends on Clusterfunk. So that's kind of the systems that we were reviewing, and these are all of different ages. And we'll touch on some of the other things this made us think of. But when we looked at the model averages, one of the things as we scroll through was just how fast.
This is the token per second output.
This is just the average token per second, right? And if we just look at the numbers, where we've got it easy to see there, the DGX and the MacBook were somewhat evenly based, but the A6000, and I think what was most surprising to both you and I was how much faster the 4090 was, even than the A6000. It's got less memory. It's only got 24 gigs of video RAM, so it's got half the memory. But the chip architecture means it moves a lot faster the way they do it. Now, the other thing to think about is the power usage between the MacBook and the DGX is probably half to a quarter what would be for those other systems, for the same level.
And I think A6000 and the RTX 4090, I think both are 300 watt peak, if not higher.
I think the A6000 is more. I think it's like 600.
Okay.
Because we were right on the edge of being able to put the pair of those in that system.
And I think the 4090, the bump you are seeing is memory is lower, sure, but the models we were testing kind of fit on that memory profile. But I think it has a faster clock cycle. Maybe that's why it's.
Well, and that's one of the takeaways that you and I had is that we need to go look at this and say, okay, one, what were the size of the models in relation to the video cards? But two was what was the what was the precision of the model, right? Because
Yeah.
we've talked about this on the podcast before. You can have a 8-point precision model, a 16-bit
Mhm.
floating point precision model, all the way down to 4. There are some people who are quantizing them less than that,
Yeah.
but I would say the performance gets really, really sketchy at that point.
Right.
Just the consistency of responses.
Yeah.
So what that all means, though, is some of these chips, like I remember in the GB10 architecture document, I think that was optimized for FP4 and FP8 in addition to FP16.
Okay.
So that's what we need to go look at and say, hey, take the same model and test it.
And I think A6000 is optimized for full precision as well. So you might see a huge bump once we kind of run this. These are all Olama based models that we were running.
Yeah. Yeah, we're using Olama to run those. So that's one of the other things we want to test. And then the other thing we'll point out is notice how much more performant the OSS, the GPT OSS model was.
Yeah.
And that gets into this idea of a sparse model versus a dense model. So do you want to cover what the difference between those two are?
So I think you are meaning sparse models are the one where you have multiple like agent, so not agent, but a committee of expert models.
There's mixture of experts,
Yes.
but then there's sparse models, and they are trained. What's the right way to say it? It's similar to with the DeepSeek.
Oh, you're talking about the sparse attention.
Yes, they're sparse attention.
Gotcha. Yes.
GPT OSS, I believe, is a sparse attention model.
So sparse attention is it's a cool concept where you are not paying attention across the board, all of the tokens that's in the context, but you are paying attention on high probability. So you run a simplistic model like a logic model on top of it and assign, okay, these group of tokens need my more attention, and you go there first and pay attention. So you're not computing the attention weights or whatever you call it across the entire context window, right? So you're focused on it. So that's why it's really, really fast, because it's not doing the additional math.
Well, and that's why I was calling this out, right? Because they ran, and this was a tool. We'll post a link to the repository we used. It was called LLM Bench, and we used it with 514B, DeepSeek R1 14B, and then it was GPT OSS 20B.
Right.
And so one of the things you'll notice, though, is how many more tokens the GPT OSS. That's the middle column here. I guess maybe you can see my mouse, maybe you can't. But that just across the board was more performant in the purple than the others. And so that was something that caught our eye. We were talking about what are the reasons why. And so that's where, again, this is where it gets complex. It's choosing your model architecture, the rest of your infrastructure all together is what drives the performance of the system. It's not the size of the model necessarily. It's that whole stack that drive all of it.
Yeah.
It's kind of back to the old days. I think I've told you this story. At one point, one of the teams I was working with needed to build a server for a JVM. At that point, it was an old WebSphere server. And it was just as like multi-core chips were coming out. So all the companies were playing with their licensing, and you pay more per core. So we've gone from single core to dual core. I think you could get quad, maybe you could even get 6-core CPUs at that point. But the question was the workload really properly optimized for multi-core / parallel work, or were you better served to go throw more clock cycles at it?
It's a similar problem I've seen in machine learning world quite a bit, traditional one, when let's say you are trying out tons of different models and your data set is massive. Even if you have like 16 cores you run, it is actually slower than running it on a single thread, because it's not doing that much IO with that huge data set in and out. It's releasing and bringing it back.
We actually ran into that in a small data set, right? That was for a machine learning model, an image model we were working on, and we were taking it from an x86 system to an ARM.
Yes.
And in the x86, we had broken up the images into lots of little pixels. And it trained really fast on an x86. We ran that same thing on an ARM, and it was taking like 3 days.
Yes.
And so you changed to something that was counterintuitive to run actually
the whole
run
image.
more data at a time.
It's not often talked about, this whole aspect of data transfer between systems, because it's got limited cache and then RAM and all that stuff, right? So moving the data is sometimes very slow compared to the math itself.
Well, it's the infrastructure, right? It's the difference of saying, hey, I'm going to make this work once versus I'm going to actually make this a production system. And it's the same reason why we were talking about the quantization, right? Because some people are going to try and take that larger model and quantize it. They may be better with a higher precision model, but smaller, right? Because it's going to give them better answers. And so that's where LLMs make this really difficult, is because now you're trading off accuracy and the ability for it to respond to the speed of loading it and the speed of operating it. And what people also mix up sometimes is what does it cost to train a model versus what does it cost to query a model or do an inference on a model. So when you hear the term inference, you're requesting an answer from it. You're not training new data into it.
And this becomes an important question. Like if you're doing something generative, like writing an email or something, that speed wouldn't bother you a couple of milliseconds. But let's say you have a LLM in your pipeline, which is ingesting unstructured data and spitting out structured data. It could be transcripts, it could be any of those signals, right, coming out of field, where you are using LLM, even if it's small LLM, if it is fast, you could get way more throughput on a much lower compute budget using, right appropriate model than throwing the biggest, baddest model you can throw at it. You often don't need that as well, right? So,
and sometimes we've seen you're actually better to run a couple of smaller models for dedicated workflows because you're going to be able to get more control over the outputs. You're going to be able to get more control over how you're doing the checking. You're also going to be able to get by with a lot less compute. So,
and those add up. So
So one of the things that's interesting too, as we think about this, is all of these are slightly different in environment, right? The 4090 has the benefit of that is a well-tested and true card, and there's lots of driver support, and almost any project you're going to find will run on the 4090. The A6000 is pretty much the same until you try and do what I did, which is you try and run two cards. And at the beginning of the year, most projects were not supporting dual cards, but now I'm seeing that in a lot of the repositories. Now with the Spark, the GGX Spark and the MacBook, now you've got a difference because the Spark has CUDA, which is a huge benefit. But it's still ARM, it's still pretty bleeding edge. The MacBook does not have CUDA. It does have MLX, which is Apple's, but it means there are a lot of repositories that either require a lot more effort to run or won't run because you don't have CUDA.
Correct. I mean, MacBook is really good for inference if you're running Olama, quickly getting a results. But if you're training or even fine tuning, that's miserable on a MacBook versus anything with a CUDA, right? All the libraries are there to just run it.
Well, and anything with image or video generation is going to be a problem on a MacBook. From what I've seen. There's some workarounds, but honestly, it becomes a data point. And when we look at these, you start to go back into when we're looking at this comparison, you start to look at the cost, right? So the MacBook with 128 gigs of RAM was about $5,000. The DJX was about $4,000. The dual A6000 box, and I did not do this as the Cadillac. We had to do a little bit of work to go build it. We did it for as budgeted build as we could. And that was about 12, 13, I think, by the time we were done. To do a new build with the new RTX Pro, which would get you 96 gigs of video RAM. That, from what we've been pricing, is between 14 and 20 grand. And your 4090 system was probably in the 4 to 5 range. 5.6.
5.6.
So that's all things to think about when you're building your performance system. And when you throw this up in the cloud, that becomes a whole different set of math because now you're either buying fractional time on someone's system or you're buying time on it. It becomes what's your time per minute. And so you got to combine that with the level of effort to get something running.
That's the other aspect of it. With newer system, you do have that. A lot of torch are not supported on the Spark yet. Last time I checked, maybe they have support now. But
it would be the same thing if you're using like some of the new AMD integrated memory systems or some of the AMD or the other Intel. A lot of these you can make run on those different setups or with those different GPUs. It just requires a little bit more effort than using some of the CUDA stuff.
The integrated memory with the Mac and the Spark you have, do you think that's one of the bottlenecks?
So I would have to look. That's a number of the articles I read on the DGX itself on the Spark said that one of its kind of flaw was its memory throughput between the CPU and the GPU or the memory bus and the storage. I'd have to look at what the MacBook is. Because I looked at it a little bit. I know that the new M5 cores are significantly faster, more memory bandwidth than the M3s, which is what my machine is. But it doesn't look like they've released the Max or the Ultra CPUs for the M5. So I'm kind of looking at that to go, okay, does that make sense? Or, I've jokingly threatened you that I'm just going to get one of the GPU docks and throw a 5090 or a RTX Pro on there just to go, okay, because I don't need it to be super fast. I just need it, once it's in the GPU, I need it to go give me results fast.
Because the memory on a GPU card, typically they are much faster than traditional RAM sticks
Yeah.
that you put in, right? I think they are GDDR5 or something. I
Oh,
forgot.
I don't
I'm not
remember.
tracking them either. So, that once the model is loaded into the, GPU memory, then it's really, really fast. And maybe that's why you see a bump in 4090, A6600.
Yeah.
It's just, if you look at the card profile, it's a 2U versus 4090 is 4U, is a much bigger heat sink. So it's running much hotter. And A6000s are data, warehouse,
Yeah.
supposed to be efficient energy-wise because you will have thousands of them.
Well,
So that could be a thing.
The A6000 usually has two versions. They've got a power efficient version and then the full, hey, how do we run it fast version? So there's the max Q version and there's the full version of it.
Okay. Which one do we have?
I believe ours are the full, but I don't remember.
Okay.
It was like a year ago when I put the order.
Yeah,
in
that's
for
true.
it. But I think this leads to, one of the next tests that we'll try and do, which is to say, take the same model and run it in different precisions on each of these.
That would be interesting.
To go see what does that do from a performance and do we see any specific bumps? Because I think that I'll be really curious about, in all honesty.
Yeah. Because often we would train it at lower precision once we have kind of figured out what we are doing with it. So it's pretty cool.
Cool. So any other last?
No, I'm waiting to get my hands on a lower precision model and test it out, see what comes out of it. So it's our drag race, right? So
yeah, we'll figure out what it is, or if there's a way for us to visualize instead of just show a Excel file.
Yeah.
But there'll be. It's going to be interesting, and I think I was just showing you if I can figure out how to get it running. Right, I just found a new video model that does like a whole multi-scene shot in like a 15-second multi-scene shot versus just a single one, which it'll be interesting. I think that will run on the DGX.
All right.
Otherwise, we'll go back to the A6000. So we thank everybody for joining us. Today was a short one, but we thought it would be interesting to share some of that data. I didn't do my millennial job in the beginning, so please like, subscribe, send us comments. Otherwise, I think they're going to replace me with a AI avatar at the beginning of these to make sure that gets said. But we really would like everyone's feedback on what you'd like to learn more about or what you'd like to hear us talk about so that we can continue building that into the podcast. So thanks all.